Welcome to this video tutorial about Trimble Business Center Photogrammetry and a deeper view into the deliverables that can be created. We will take a closer look into the different settings about defining the point cloud, especially about the point cloud densities, but also about the auto mosaic that will be created from. And we will here in this video take a deep dive about the digital terrain model. The digital terrain model is using a feature-based matching algorithm, and it is working in a classic way, which means after the point cloud is generated, we create from this terrain model, from each single drone image, an orthophoto, which is a smaller portion of the original image, because we don't need the full image. We can just focus on the center part of the image, and which means if we have 1,000 images, then after this process we will have 1,000 orthophotos when we select the whole area. But this is all happening in the background in the temp folder. And then from these 1,000 orthophotos, which are a smaller portion, as I mentioned, it's more the center part of the images, then we create automatically seam lines, because these orthophotos are still overlapping each other, and then these seam lines are fully automatically created and used afterwards to merge, or to, in this case here, create a mosaicing approach, so to blend these 1,000, in my example I use 1,000, these 1,000 orthophotos into one single ortho mosaic. And if this one single ortho mosaic is below 4 GB of size, then it will stay one single mosaic. If the size of the final mosaic extends the 4 GB size, then we are automatically tiling it into the smallest amount of pieces, and still with the main rule that the ortho mosaic, the pixel is facing north, and then this will be our final result. And this is then in the digital terrain model approach, this is then organized by the create ortho mosaic resolution. So the ortho mosaic resolution for the digital terrain model approach in this case is individually definable and therefore also possible. Okay, so let's take a closer look at the density levels. So we can choose for the point cloud density low, medium and high, and this has also an impact on what resolution we are running the point cloud extraction. So when we are using point cloud density high, we are running it on our full resolution of our dataset. In our example here, we can see one pixel has 2.7 centimeters ground sample distance, and this means also for our point cloud density high, we will run it on this 2.7 centimeter image. If we choose point cloud density medium, we will run it on permit level 1, or some people call it minification 1 in this case, which means 2 by 2 pixels are resampled in one single pixel. So these 2.7 centimeter ground sample distance is resampled into an image with 5.4 centimeter, which means it's only a quarter of the size, a quarter of the amount of pixels, which is then also a faster process, but no surprise, our pixel size is only half the size, and therefore also our quality will be, in this case, lesser. And if we would run the point cloud density on low, then again 2 by 2 pixels from level 1 will be then reduced into one single pixel, or if we compare it to the original size, we can see here 4 by 4 pixels are then reduced into a single one. Therefore, our resolution is 10.8 centimeters. We have only a 16th of the data size, so it's a much faster process, but again, the accuracy in position and height will then be, for the point cloud, worse in this case here. Okay, so let's focus now on the height quality. So again, same values. Our ground sample distance is 2.7 centimeters, and we are now only looking here at these green rows. So let's start with the DTM high. So our ground sample distance is 2.7, and then typically we say the height accuracy is 2 to 3 times larger than our height accuracy, which means here 2 to 3 times sigma. So in our case, we see here in the protocol, we did have here for our terrain points an average height accuracy of 3.5 centimeters, which will then mean if I multiply this by 2 or 3 times, so in this case here, this is the Gaussian distribution, that's why I use it here, 2 to 3 times sigma. So typically it's the most amount, 95% of our data is 2 times sigma. So this means in this case the height accuracy should be something, for the most amount of our data, 7 centimeters. So because on DTM high we are matching on level 1, so that means our pixel size is only 5.4 centimeter. Therefore that's why I here entered here 4 to 6 times the sigma from this value here. Typically when you run your protocols, then in this case here you would get here already a different value, and then you could then see here this part for the DTM generation. But this value here is from the block adjustment, so don't look for this. There's a in the temp folder that we have here similar values. Okay, let's make it here clear. So for DTM medium, we will only reach 4 to 6 times this sigma value, which means in my case 7 times 2, so 14 centimeter height accuracy, but it could also be in this case 21 times. Yeah, so some in this range. So 95% will be around 14 centimeter for this data set here. And then if we go to low, no surprise, we have now 8 to 12 times. So in my case here, the height accuracy will be then something around 28 centimeter in height for 95% of my data. Okay, additionally to the height accuracy, we are also automatically using a different point density. So for the DTM high, we are matching every 30 pixels a point. So 30 times 2.7 centimeter, in this case here, ends up in 0.82 meters. So every 82 centimeters in the DTM high, we will get a point in our point cloud. For DTM high, we are using a more sparse approach. So we say every 60 pixels. So 60 times 2.7 centimeters is then something around 1.64 meters, and for DTM low 120 times, so every 3.28 meters a point is generated into our point cloud, which has then also an impact of representing smaller details in our terrain or our area of interest. So therefore, of course, a denser point cloud can better represent steep hills or steep hill changes, so slope changes, smaller details in the terrain or in our area of interest. Okay, so let's take a closer look now in our reality. So this is now our auto photo generated from a digital terrain model approach. Let me go here to our deliverable settings. So this is now here created with DTM high, and our resolution used here with 3 centimeters. You can check this always. So in case here, I have here my auto photo. If I click here on the properties, we will see here the pixel size is written with 3 centimeters, and we see how many pixels this mosaic contains, and also the size where the data is located, and also our upper left, lower right, upper right, and lower left corners are here in this project. I named in this case here this already a DTM high auto, which means I used for this one a DTM point density with high. So let's take a look on this point cloud high. So here is my DTM high point cloud. And if I go now here into an area and I switch off here my auto photo, then we see this is our point cloud. Let's take here in a 3D point view this area here, and when we go to the same part where our here is our excavator, so this is now here our area, and this is the point cloud representing this part. And we can see here that the excavator here is not represented in full detail. Also, when we look here at these, let me here pan a little bit to the right side, we can see a little bit here the boxes, but here on the ground, these objects, let me go here to this part. So these objects here, they are not displayed in full resolution how they should be. And this is exactly what the digital terrain model is trying. It tries as good as possible to avoid objects off the ground. It tries already to represent a ground model. Now, if we switch now on the DSM model here, we will now see that this DSM model here is now sorry, not the auto here. If this is my DSM model, then we see here that these objects are now all included. So the digital surface model approach really wants to keep here these objects above ground included. So again, let's go back to the digital terrain model. So here it tries to avoid them in this part. This is what this algorithm includes automatically. So this is something that is the main goal. And therefore the digital terrain model is, as we saw in the first slides, it is a very fast algorithm, especially when you run it on medium or low. And it also tries already to represent the true ground in its point cloud. So let's take a look also just to here be sure. So let's go into this area, switch off the orthophoto. Let me close this one here. And when we now calculate here the distance from one point to another, then we would see now hopefully these 0.83 or 0.82 centimeters. So this is now here the density of this point cloud. The height accuracy here should be something around 7 centimeters, but only representing every 82 centimeter our terrain, which means if we have here fast changing slopes, then of course this is, let me perhaps see if we can here make these points thicker, extra large, but no, the orthophoto is in this case here overlapping here, but we can here, if I switch it quickly back and forth, you see I cannot represent every possible position here of this edge, and even when this gets more squeezed, more smaller, faster changes, then this point cloud will not be able to represent here the details. But our orthophoto is now representing every 3 centimeter a point, and therefore here is our highest resolution. What we can do now is run the whole process again. Let me here go again to the deliverables, select that our point cloud is generated with medium, but our resolution stays here also still on high. And this is totally fine. It means only that our terrain model is in this case here using only every 1.6 meters a point. It will have a height accuracy not of 7 centimeter but around 14 centimeter. But still I have now an approximate terrain model, a bare earth terrain model, and then this bare earth model is then our representation to create the orthophoto. And this is exactly what we can here take a look. And when we now switch on our DTM medium, then and then we switch off the high. So let me here make it here this way. Yeah. So now you can see here that the resolution is in this case here the same, but in this case here, because we only have every 1.6 meter a point, this is the first thing, and secondly we only have 14 centimeter height accuracy, then there is still a positional difference between these two results, but not in the resolution. It's still every 3 centimeter in orthophoto. It is also not more blurred. It's really here just that in, and this is very clear. We can take here a closer look and see this also. And we take a look here. This is now our point cloud high. And when we now here switch on to the medium, then we can see now here that in the medium, because the density is not so strong, it will even exclude furthermore in between objects. Yeah, so these smaller objects in between the buildings at medium, we can still see that they are not totally eliminated, but we have here a smoother ground. It's not better. It's just that in this case here it's more smoother. Probably the high is better. It will have a more detailed position in smaller features. So for example, we can see it here very well here at these edges of these ridge lines. But in this case here, it still allows us now to generate an orthophoto. And this is then seen, for example, very well on these buildings, or this here flat roofs. In the medium, this looks lesser bended as if we take a look on our high. And this is very clear because the high model has typically here also some data running on top, and the medium here already has filtered out and is already on the ground, and therefore in the medium the truck looks better in this case here, and therefore causes here the difference. And then of course same thing happens then for the DTM low orthophoto, and we switch on this one here. Then here we see even further that objects in this case here are nicely auto-rectified, but and now we see here a larger difference in position movement for our ridgeline. Yeah, so you see here the ridgeline is moving much more drastically, and the reason is, of course, no surprise, our point cloud now here in the low one, let me switch this one on, is now here much more reduced. Yeah, we see this here is almost completely gone and missing. So if we again switch here off the high point cloud, then we see here this is missing. The buildings should now look a little bit better. Yeah, it's not that they are better, but they will in this case here probably here in the DTM low. Exactly, yeah. You see they are lesser bended here in some parts. In the DTM high, they are much more bended because the point cloud, of course, is here causing these troubles. Yeah. But on the other side, we will lose details in these slope changes. Yeah. So here, definitely to be seen that, sorry, opposite wise. That, oh, here, DTM high, DTM low, here, that this is causing here a misplacement. All of these DTM approaches all have the disadvantage that they are not truly auto-rectifying. It means if now I switch on my my orthophoto generated from a digital surface model, and we take a look here at here this object, for example, here. So let me here stay with this one here and then switch this one on. Then you see now that the machine here is truly auto-rectified. Yeah? So I can see here behind it. Let me here also go here. When you look here behind this box, if I took the DSM, then in this case the box is truly auto-rectified. And then I can see also the content in between. But because this is a pixel-based approach, and therefore the image or the orthophoto looks a little bit lesser radiometrically equalized in this case. Yeah, so this is then just based on that we are here calculating from a 2.7 centimeter pixel-based SIF operating algorithm, and then we generate from this 2.7 centimeter original true orthophoto a 3 centimeter true orthophoto. This is where we now accept it, say this is really, we want to get 3 centimeters when the person asks for 3 centimeters. If you would love to have the pitch perfect solution, then it would make sense to go to the create deliverables, and when you go here and let me see if it shows to me here also. Let me just break and show it then. So here we go. Then you could here click into this one here and then change this here and say 0.027. This would be my original resolution. And then when I click out, then this value is here written. You can also go in and let's make a totally wrong value. Let's take 0.01 and then I click somewhere else. Then it will tell you, look, this is not possible. The maximum that we can offer you is 0.0225. Therefore, this is the range that you can only use. If you do this for a digital surface model, again, then of course, and now this is the big difference, you need to select from the digital surface modeling also high, because this point cloud is now used to create this true orthophoto. There is no in-between step where we use the point cloud to generate from 1,000 drone images 1,000 orthophotos. This is not happening. In the digital surface model, we are generating this point cloud, and for high, this means for every pixel. So for every pixel, so for every 2.7 centimeters, we are creating a point. And then from these 2.7 centimeter density point cloud, we are using then, this is now a little bit more complex structure. There's a DSM and then a texturing, and then the texturing is based on a specific model, and then this model is then used to extract our true orthophoto. But this is now our base. So if you choose here a low density, then this is for a digital surface model. In this case, every, let me just double check that I don't say something wrong. So this would then be for DSM low, it would be every 4th pixel a point, and therefore this would then be every, if I take 4 times 2.7 centimeters, then it would be 11 centimeter density. And of course, if you have 11 centimeter density, then creating a true ortho from it means all these pixels in between are not covered from the point cloud, and you need to have a point cloud value to generate your true orthophoto content for digital surface model. So therefore, for DSM, you should really always stick with the resolution, which means if you select digital surface model low, then please also use the low resolution, or at least you remembered my slide, you could enter here 11 centimeter in this case. If you take medium, then in this case take medium, or based on our slide, so in this case 2 times 2.7 centimeters, so 0.054, so I will round it up, or you enter 0.054 as a resolution. And if you take high, then you can now go here with your 0.027. But in the end, that's why because this is complicated and not everybody's watching this video, and whoever is watching until now, thank you for watching until now, really try to stick low with low, medium with medium, and high with high, and then at least you're in the right range for digital surface model. You can, of course, like I just showed here, calculate what resolution you could tweak to the best. But this is just that you are aware how this works. And there's also a large philosophy behind it. I mean, this is a good reason why we are doing this, and the main reason is for mapping purposes. So if you have to cover huge areas, then typically you generate an ortho mosaic for your planning and for design. And then, of course, I would strongly go with a digital terrain model. And now it depends how fast you want to get your planning devices and your data. So you can run it on low, medium, or high, depending how much content of terrain you want to have included into your point cloud. And then when you say, okay, this is for me fine, I take a medium approach, so only half the resolution of my images, half the resolution of height accuracy, but and therefore I will then create for me here for my design purposes an orthophoto with 5 centimeter. Then you can just enter here your 5 centimeters and then create from these point clouds this auto mosaic. And this is what the digital terrain model has a big advantage about any other product that is on the market here. It really allows you to create here very fast auto mosaics with a good quality. Not as good as in this case if you would run it with digital surface modeling and a true orthophoto, but for many CAD design parts this is totally sufficient to calculate. The only thing you have to be aware is then when you take here medium, it's every 60 pixels, or here low every 30 pixels, and then you have to decide if this has an impact on the positional accuracy and of your for your drafting and plotting, and therefore if this is important, then go with high, which is still much faster as if you would run any of the digital surface model approaches. This is really here a much faster process and still gives you a lot of content to work with auto photos. Okay, so I hope this gives a good introduction, or not introduction, a good overview and deep dive into our deliverable possibilities of German Business Center Photogrammetry. And I wish you a good day. Goodbye.